Okay, we're going to have this morning's presentation recording. And again, who is zoomafm.com. We are several former employees of Agilent Technologies, and we want to team together to support a customer for their Agilent AFM for the next 10 years. And I see there's a couple of new people joining in, and you have your instrument that I think some of you are first time come in. And this is a great opportunity for you not only to listen to the lecture, but also most importantly, you can ask us questions and then you can talk to me and talk to other support engineers here. So again, the banner on the bottom are the email address, the website addresses you can find us. And on the left corner, you have the YouTube channels that you can find the recordings of all the old presentations. The reason that we will give the presentation a little bit short, that's because I tried to make this event as weekly, so it's very easy for you to find us. And in case you have a problem, just I try to do everything in the same time. Okay. Again, these are the couple of websites we have: zoomfm.com, the meeting gathering place. And NanoQ Technology is where I put my inventions. And then OnQ LLC is the business of Steve Raba. He is the repair service engineer of Agilent Technology, and now he can repair your hardware. Sample preparations, today's topic, sample preparation. About 50% of your effort of having a good image using atomic force microscope is actually sample preparation. And I have seen people have spent a lot of time trying to optimize a lot of things, but they're working on a sample that is not in good quality, or they have the wrong sample pairing with the wrong tip, and so on and so forth. So sample preparation is a kind of art that sometimes get lost after student graduate, and then the next group of students don't know how to prepare the samples. So there's some, and also there is no like fixed way to do that. There's many different ways, but there's just a bunch of principles and attentions that you have to pay to make your sample the best quality. So there are a couple of principles you always stick to when you do sample preparation. These are the basic principles. I always take out these basic principles before you ask for any suggestions of how to prepare a sample. The principle number one is you have to separate. You have to separate. If you want to see one snowflake, you have to separate that snowflake from a pile of snow. And then principle number two, you need to have a flat background, just like photography. And your background need not to contribute to the topography. And then, as I said, if you want to see something that's very small, your background has to be really, really flat. And principle number three is very important. And a lot of people complain about their samples always slightly drifting, a problem of fixing it. And then that's because sometimes immobilize the sample onto the substrate is not proper. This immobilization sample onto the substrate. Again, there's a lot of publications. If you want to see something, AFM, again, it does not look at a species. AFM touches it. And when you touch it, the molecules or particles cannot move. If it moves, you will see something that it does not make sense. And then the image itself will have some of the twists and the elongated tails. That's the result of the immobilization failure. And principle number three is avoid any source of drifting, creeping, and peeling. That is not the immobilization. It is how to fix your sample on the stage of your AFM. And that's equally contribute to a lot of successes and failures of imaging. So, okay, first principle, separation. Again, I will put a snowflake here that if you want to see the snowflake, and you cannot see a snowflake in a pack of snow. Same thing that you cannot visualize a nanoparticle if a nanoparticle is mixed up with lots of nanoparticles, mixed up with a lot of things. So you have to separations. there's many different ways to do the separation. How do you do that? For example, if your sample is made of molecules or nanoparticles, and then your sample appeared to be a little bit too condensed, and then you don't see your sample basically, right? You usually want to see your DNA, and then you complain, I don't see the DNA. Why I don't see it? That's probably because the first failure of your sample preparation was, which is the concentration is too high. So here you go, that the first principle of sample preparation is actually pay attention to your concentration. Your concentration cannot be too high. Typically, to form a monolayer of any molecules on an AFM sample, anything, it takes ppm or ppb. It's extremely low concentration. So so if you wanted to see a DNA, that you have to have like, micrograms of DNA samples, you have to dilute it 10 times and 100 times, dilute many times. So achieve very low concentration. That's one way. Second way to achieve separation is we call it charge-based separation. Charge-based is that if your molecules are basically have negative charge or positive charge on it, okay, if you have charge on it, and then those molecules or whatever nanoparticles, they start to repel each other. They start to stay away from each other. So charge-based separation can also achieve separation. And then some of the things that is naturally charged, some of the species are not naturally charged. You have to pay attention to its pH value when it's liquid, and so on and so forth. So for example, protein, and then normally they in a certain pH value, they are charged and they repel from each other. Charge-based separation. You could also using solvent dispersion for nanoparticles, colloidals, nanotubes. It's actually relatively simple that you put your sample, dissolve them in organic solvent, for example, ethanol, and then you look through it, and then you could dilute it. You could dilute the solvent. You use the solvent to separate them. Basically, when you put a nanoparticle or molecule into the solvent, dissolution, basically those molecules in the liquid solvent will attach and attract to your molecules or particles. And when that happens, it separates them. So your solvent dispersion is a very good way to achieve a good separation between particles. Sonication is a good way. And if you want to dissolve something like that's for example, starch, right? Starch powder, it's a kind of powder. How to dissolve them in water? And they put in water, they clump to each other, form little globes, like piles, little particles there. You could use sonication and put extra energy so they vibrate and then separate from each other. And sometimes you can use a dried air jet stream. I'll show you some examples later. Second basic principle is choose a clean and flat substrate. Again, if you want to see a tree, you see the tree very clean when the tree is on top of flat terrain. If you are looking at a mountain full of trees, then you don't see individual trees. You cannot measure its height because the trees are everywhere. So you have to have a background, right? And then if you see particle on the lower right corner of this image, basically it is not a particle, but you don't see a nanoparticle. That's because look at the scale. It's 20 micron scan. So you're actually looking at a sample packed with those nanoparticles way too much, and they dry on the surface. And then because you don't see individual ones, you zoom out to 20 micron. So you're literally looking at a top view of a mountain, and then you're trying to wonder why I don't see trees, why I don't see the sand on the surface on the ground, because you're zoom out too much, scan area is too big, and your sample are not separated, and the background is not flat. The upper right corner is a very nicely prepared sample that have a flat, clean background. So substrate immobilization, mounting, and position. So we're going to look at the immobilization after you achieve the separation immobilization. So here, this is 5 nanometer nanoparticles on clean surface. And then this is these two data actually come from the same day, same sample. The second image on the right here to have something a little bit bigger than the particles. That's because we use a piece of glass that's not cleaned. Not clean. So what do you see here is a dirty glass, and then then at this point you cannot tell it is nanoparticles or not, right? You cannot tell. It's because one problem of atomic force microscope is that it sees everything, and then you say that you want to see my nanoparticle. If a substrate is not clean, then it's difficult for you to draw a conclusion that there's nanoparticles on it. So the last presentation, if you look at the YouTube, you can find it, is about how to prepare a lab. And then, as I said in the last presentation, if you don't remember, is that in a good AFM lab always have a big collection of this substrate. It is a Moscovic mica. It's a layer style structure. It's aluminum oxide and silicon oxide layered crystal, and then between the layers, there are no covalent bonds, and only some potassium ion is trapped between layers. So if you add a little bit pressure between the layers, these layers will separate and expose the surface of the surface of mica. And because the surface of mica is just being exposed to the environment, so it is clean. It's a guaranteed clean. It's very clean, atomically, molecular level clean. So when you clean the mica, it is clean, at least for a certain time. Very flat and very clean. So you can use that substrate to put your sample on, immobilize a sample. So if you have run AFM on a mica surface, if you scan a micron or several microns, some people complain, oh, I don't see anything. That's correct. You don't see anything because there's nothing on it. This is great because anything you put on the mica will show up because your background is so clean and flat. Several characteristics that I need to mention to you about this mica. One is that mica surface is actually negatively charged. The surface has negative charge in pure water. And then, but you can turn into positive charge. Later I mention how do you turn the surface into positive charge. So it's a flat surface, hydrophilic, and it's negatively charged. The only problem of mica surface is it's not conductive. So you cannot do STM on it. All right, here's a couple pictures of how to clean a mica. I intentionally showed you a mica that is very dirty. There's a lot of things on it, disgustingly gummy with some black things on it. How do you clean it? Right. So this is the one good thing about mica. It's clean, is very persistent, very consistent, and very easy. You take a mica and you pull out a tape, Scotch tape, and then rub the tape on the surface of that mica, and you peel your tape off and expose the sample. You don't need to have sample the overall. It's very clean everywhere. You just have to clean the middle because that's all you need for an AFM image. And then you have clean mica, and it's guaranteed. Okay, so there's another examples of sample deposited on mica surface. This is a DNA sample. It's a lambda DNA, so it's a DNA pieces. Okay, DNA pieces, and then the DNA pieces. This sample is prepared so that you dropped the DNA. First of all, DNA is dissolving water, and it dropped this water DNA onto the surface, and it blow it with dry nitrogen. So when you blow it, it dried the water very fast, and you also stretch the DNA out. So DNA is stretched out and separate from each other very nicely. Okay, so just drop the DNA on the surface of mica. You will create a sample that is a lot of aggregates, and sometimes you don't even see DNA. And this is another sample that I did not use the jet. I just dried it on the surface. No, actually, I did not dry it. I dropped the DNA on the surface of mica and then rinsed it with DI water. One thing about AFM is that it is extremely sensitive to anything. Everything on the surface, it will show up. So in other words, it is extremely important for you to have very clean water if you want to use water and let it dry on the surface. You need to have the water extremely clean. The water cannot even touch anything. Right after the DI water machine, you use the most clean glassware. The glassware has to be properly cleaned. And then you rinse the surface after you drop the DNA, and then you image. And then during the rinse, that you wash away the excess of DNA, and after that you blow it with dry air. Blow it so that you accelerate its dry procedures. Okay, talk about the charge on the surface of mica. Mica surface in neutral water, it is actually negatively charged because the hydroxyl will attract proton. You actually lose a proton, and then the surface is negatively charged when at the pH value of around neutral. 6.8 is neutral. And a very strong acidic liquid, the surface will turn into positive because in strong acid, there's excessive proton or hydrogen cation in it, and it'll be attracted to hydroxyl and adhere to it. The surface become positive. So in strong acid, pH 2 point something is very strong acid. You can dissolve a lot of things in it. But in a clean water, it's negative. So this is an example of using the negative charge to prepare a good sample. This is a standard sample. If you want to practice your AFM image skill or diagnose any problems using AFM, I suggest you use this sample. This is called ferritin. Now you can buy these ferritin samples from Sigma Aldrich, and it's very easy to prepare because those ferritins are very strongly positively charged. So if you drop a ferritin solution on the surface of mica, rinse it right away, and you can image them in water, and it's a very nice sample. If you want to image anything of organic or biological species in water, in liquid, you have to practice imaging ferritin on the surface of mica in liquid. If you cannot do this, other samples are much more difficult. Here's another very good substrate I suggest you to use, and that's the HOPG, graphite. Graphite, one of the characteristics of graphite is it is a very easy to clean substrate, very easy to clean. That's because graphite is also made of sheets of graphene, right? Sheets of carbon honeycomb structure. And between the sheets, the bond is very loose. So if you use a tape to remove the top layer of the graphite, the surface is clean. And graphite has two more interesting and useful characteristics. One is graphite is hydrophobic. So you can actually, using hydrophobic attractions, using graphite to prepare a sample like a protein sample, which is sometimes a lot of proteins are hydrophobic. And another thing about graphite is it is conductive. So you can run scanning tunneling microscope on a graphite substrate. So graphite is atomic flat, clean, hydrophobic, and highly conductive. Again, here's a couple of picture procedure show you how to clean your sample. Right, you have a piece of graphite. Again, put a tape on it and peel off, and then you expose the graphite. Here's an example of the graphite after being peeled. The image on the left is the AFM image on this graphite. You can see these steps. Okay, atomic step is very useful. It's not just some kind of defects of the sheet on the surface, because if you see something that is totally flat and nothing on it, sometimes you cannot tell. You don't have an image or you don't have anything to see. But if you see a atomic step, that's great because now you know your instrument is working. Okay, and then second thing is that if you see a step, you can measure how sharp is the step. That's because the atomic step is atomic sharp. It's very sharp. It's one atom wide. If your AFM tip is not atomically sharp, it has a certain size. So measure the width or how sharp it is. The step can tell you how sharp is the tip. Okay, and that image on the right is a sample that people often run to test the ultimate resolution of your AFM. This is a tapping mode image of a C60 carbonyl, C60, C60H122 on HOPG. They will form a self-assembled organized layer. And then after you formed a layer, the surface, you could actually image, and you can see these nicely aligned atomic layers side by side. It's a good way to test the sharpness of your tip and your skill. And sometimes people use this image to challenge some AFM, say, hey, if you're high resolution, how come you cannot see atomic arrays or molecular array of this sample? The reason that in the early time, the AFM scientists using this image to challenge each other is that here's a trick story. It is not always the resolution of the instrument or sharpness of the tip that matters. It also matters is that where do you image? Because these self-assembled C60, they're not always naturally formed. They formed when this droplets of C60, it's when it's flat, not when it's like a bulk. So if you see a bulk, like a little beads on the surface, you image on it, there's no assembly. Only in the flat areas, you can see those assembly. Here's another very interesting substrate that people use to in AFM image, which is gold 111 film, gold film. Now, the reason people use gold film is that you could actually clean it in a very different way compared to HOPG and graphite. And also, the gold surface have a very rich chemistry. You could grow something on the surface of gold much easier using thiochemistry. And then using the thiochemistry again to modify the terminal functional group. So you can modify the surface of the sample and achieve any kind of functional group as you want. As this lecture series proceed, I will cover this terminal functional groups chemistry on the gold surface. And today I'm just going to show you a gold substrate itself, right? It's a gold substrate. Okay, here on the right lower corner, I draw something that I put a drawing of the imaginary view of the gold 111 surface. Basically, it's a bunch of balls, gold atoms. You can think of them as balls. And then you pack them together, it'll form a hexagonal structure. And then second layer can pack on top of the first layer. Between the first layer and second layer, you can see there is a step. That's the atomic step. And this atomic step is only 2.35 angstrom thick, or 0.23 nanometers. Okay, so that's the step. If your sample is clean and flat, steps is everywhere. Okay, so if you can see the atomic steps, you know your AFM is good, in good working order. That's first. Second, and you know your surface is clean. If you do not see the steps, either your imaging parameter is not right or your surface is not clean. You know, you see that the image on the left upper corner. How do you know it's clean? It's very hard to tell it's clean or not. But you look carefully, there are steps somewhere, right? Now you measure the height of the step. It should be 2.35 angstroms. If these are 2.35 angstroms, then you know your surface is clean. So let me talk something about the thiochemistry and the reason that we use gold as a substrate. So thio is a molecule that you have carbon chain. At the end of it, you have SH, thio functional group. This SH can react strongly with the gold surface. Other precious metal probably works too. The attractive is very strong. It forms a very strong covalent type of bond. And when this happened, the molecules, the more and more molecules attract to the surface, and then they actually form a two-dimensional pack of crystal. They actually form a crystal. These molecules they actually stand up and form a crystal. And so the older surface of gold will be replaced by this molecule, and therefore any contaminations, pollutions will be replaced. That's very good. That's very awesome. Then you just basically covered up all the gold, and then you look at the terminal function groups. The only thing that exposed to the interface are the terminal function groups, in this case, CH3. So if you form a self-design monolayer on the surface of gold, the surface is very hydrophobic and is very, very clean, CH3. Okay, so this is on the left corner is the device that people use to make a thin film of gold 111. Basically, it is an evaporator. It's a vacuum of 10 to negative 7. And then mica is heated at 500 degrees C. And you have a bolt made of tungsten, and you pass a high current. So the bolt is red hot. And you put some gold slug into that bolt. And then the gold will melt. And then at a certain temperature, the gold will boil. They literally boil. You can see that actually rotates. And then after that, the gold becomes vapor. The vapor will be deposited on the surface of mica and form droplets. And then at 400 degrees C, you anneal for several hours. These droplets, they form a flat surface. The one on the right, the gold surface. You can see there's a lot of cracks there. That's very, very natural for the gold surface, is because that as you evaporate and grow the gold droplets on the surface, they grow tall. But between the two droplets, because the orientation is different, they actually don't fuse together. They actually still maintain its separate grain. And then a good sample, these grains are very big. A bad sample, the grains are very small. Okay, so this is the surface of gold 111, and you can use that as a substrate to do a lot of your chemistry. However, a lot of time your gold surface is not very flat, and because your temperature annealing is not right, something's not right. As a matter of fact, when I started my career with self-design monolayer research when I was a graduate student, I have a lot of sample look like the one on the left corner, a lot of smaller grains. There's no flat surface. So which makes it very difficult for you to find atomic steps, zoom in, and do AFM STM on it. Okay, so there's another way to do a sample. That's one. The second is that gold surface, when you expose the gold surface to, say, your ambient air, it attract a lot of molecules from the air and become dirty. It becomes dirty very quick. About an hour, it becomes dirty. And then you can actually visualize to see the atomic step is visible at the beginning and gradually it's not visible. That's not because the atomic step disappeared. That's because the surface is gradually attached a layer of contamination. So at the beginning of my career study, self-design monolayer, I will evaporate in gold and do AFM on it right after that. So you evaporate gold every time you want to do experiment. And those gold slugs in the year 1997 was $50 a piece. Now it's $200 now. So it's expensive. And then you basically, the gold is dirty. And what do you do when the gold is dirty? There's actually many different ways to treat your substrate and then reuse it. So you don't have to do the evaporation every day. It makes it cheaper. One way is we call the ultra flat gold substrate template. So here's the procedure. So you have mica, and you evaporate gold on the surface. The yellow stuff represents gold. And you can glue a piece of glass or silicon on it using epoxy. Just glue it. And then you don't just glue one piece, you glue a lot of pieces. So every time you evaporate a piece of mica, it's a large sheet of mica, and you glue a lot of little coins of silicons on it. And before you use it, you bend that mica, you strip a piece out. Okay. Now you expose the gold surface that is flat and that's clean. And this works very well because you can make 50 pieces of sample and then use it as you want. And it gold is clean and it is very flat. So you use the flat part. So here is the procedure. You have a piece of gold on mica. You put a drop of glue. The glue is something on it and strip it, and then the gold is stripped away. So that's a very good substrate. There's another way I've been promoting, try to get people to use it, which is precious metal beads. So here's the one on the left it's a magnified view of a piece of gold wire, and then you using your hydrogen flame to burn it, heat at high temperature, and at high temperature, the gold will melt, And then as you melt, it shrink it to a bead, and then you let it cool down. The bead is as small as 2 millimeter, as big as 3.5 millimeter. If you look carefully at those beads, they're actually not spheres. They're spheres with facets on it. And using optical microscope, you can actually see those facets. Those facets are flat. The facets is actually the gold. It's the 111 crystal's orientation surface. And that surface is actually quite flat. And then if you prepare the correct way, it's quite clean. So that's a good way to do that. Of course, I mean, there's no AFM company makes a liquid cell that holds the bead as the substrate, but I made something. And if you go to my website, you can see some of the gold bead liquid cells that you can do. So this is not this is a piece of silver. I didn't find gold at that day. I just burned some silver wire, make a bead. Since we mentioned something about flame, fire is a very good way to clean anything. It's a good way to clean glass, and it's a very good way to clean gold substrate. The one on the left upper corner, that image, I collect that image when I was doing a demonstration in University of Illinois, Urbana-Champaign, and then open up a piece of gold, and then it was clean. And after 45 minutes, this is what it looked like. Those little grapes, they are not gold. They're contaminations from the air. I just watched them grow on the surface. And then what are they made of? It totally depends on any restaurant within a mile radius. So those are probably probably those organic molecules that evaporate from the food. If you can smell it, the gold will collect them on the surface. Now, how do you get rid of it? You cannot wash it. There's no liquid clean enough to wash. After you wash, it becomes more dirty because your water is not guaranteed clean, right? So one easy way is to burn the surface with hydrogen flame. And this is actually very simple. That you have a hydrogen tank, and then you have a glass pipe, and then you hook up a soft tube, and then just ignite the hydrogen and adjust the flame and sweep the surface. And then after a couple of sweep, the surface is very, very clean. The one on the right upper right corner was just being cleaned. Super, super clean. You can see atomic steps. A good way to clean anything is to burn them away. Sometimes you can use glass substrate to deposit your species on it. But one thing about glass substrate is that depends on the quality of it and how it was made. There's no guarantee the surface is very, very flat or homogeneous. Just be careful when you use glass slides. You have to image the glass slide without your sample. Just don't take a glass slides and then say, hey, I'm put nanoparticles in it, and then I'll image with my AFM, right? What's wrong with this procedure? That's because you don't know what you look at is nanoparticle or the particles already on the glass slides. That's because glass slides is a glass, it's amorphous, and there's no fixed crystal structure. So whatever show up there, it's there. There's no guarantee. So you have to image when it is blank, and then if it is free of the things you're looking at, then you can use this as the substrate. Okay, so it is what is next? Immobilization. That we can still cover immobilization. So immobilization, just exactly what they show this picture, is to fix your sample on the surface. And so when you imaged with your tip, when you AFM tip to image anything, the tip is actually touching your sample, and then your sample has to be immobilized, so it does not go away when the tip is touching it. I just said before that the microsurface has a charge, negative or positive charge, depending on pH and how to use it. The negative charge can be used to attract something that is positive. For example, lysosine resides on the surface, on the protein, the lysine, the NH3, the aminos. They're positively charged, and then if they're positively charged, they actually been attracted to the mica and then attached to it, form a very strong static bond, and then you can image that way. But what if your sample is also negatively charged? How do you do that? For example, DNA. DNA is negatively charged. So you put DNA on the surface of mica, they don't attach very well. Okay, so the way to do that is to use bicovalent metal cations. For example, magnesiums or nickel, sodium even. And you treat the surface using these metal cations, and then the metal will be attracted to the surface, form very highly packed layer, and turn the surface into positive. This way, if you put the DNA on it, DNA or RNA, it's actually attracted to the surface and being immobilized. There's other ways to immobilize. For example, in this case, you can treat the surface with alkoxysilane, APTES, alkoxyaminosilane, and you evaporate them on the surface, and they will form amino. This amino will attract, form bond with proteins, and you can use that to immobilize. Okay, so it is 11:40, and again, the primary purpose for me to give this speech is not to give speech, just to give a speech, but also give you a chance to ask us questions. So this presentation is 100 pages, and it was made to cover several of these sessions. We'll continue next time. Right at this moment, I'm going to stop, and then if you have any questions, please unmute yourself and then ask us. We will do our best to answer. Thank you for your time. So if you have a question, you can ask. Same time, I'm going to ask a question for Steve. Steve, are you there?
Yeah, I'm here.
Okay, so it was very nice that you gave the talk last time about the calibration of the controller. And do you have more such calibrations? For example, the calibration of sample XYZ and so on and so forth.
You mean like calibrating a scanner?
Calibration scanner, yes.
Yeah, we can go through those processes.
Okay, so if you want to do that, I have the standard sample. I can still set up. I have a sample that have those 500 nanometer grids, and I have a scanner need to be calibrated. I can set up that way, so you can walk me through it. What do you need me to prepare for other than a sample and a scanner?
Really, that's all you need.
Okay, yeah, that we probably should do a scanner calibration in our next session and record
Yeah,
it.
the scanner calibration process is extremely simple to do, but tedious and takes a long time. So
Okay,
we would be able to cover maybe the basics of it, but fine tuning and the the scanners are super sensitive to things like speed and size, and there's just a lot of different variables. So it's always best to make sure that if you're taking precise measurements, you want to first calibrate your scanner at the size of the scan you intend to measure at. For instance, if you calibrate a scanner at full range, we'll say we're using a 90 micron scanner, we calibrate it at full range. If you're going to be using that scanner to measure things with only a 10 nanometer overall range, you need to calibrate the scanner at that 10 nanometers. So it's very important for AFM users to understand that when they're imaging their samples, they really do need to be very familiar with how to calibrate the scanner because it really should be done at the scale you intend to image.
I see. So it's probably a good idea if this AFM has multiple users, you should create your own calibration standard. So you create multiple standards even, and so if you want to do certain things, you pull out certain calibration files.
Yeah, absolutely. You should definitely have the calibration files for your intended use and application. Um, keeping in mind things like rotating the scan also impacts your calibration.
Right. Right. Yeah. So I probably get myself prepared by image it and then rotate so it's actually orthogonal before I start, and then you can run through the calibration of scanner. So we have a recording of this topic.
Yeah, and it doesn't need to be perfectly orthogonal. Just understand that you can't use the rotate feature in the software. If you use the rotate feature, you will need to recalibrate at that rotation.
Right, right. When we say rotate the image, we're saying using your fingers. You take the sample
Yeah,
out and use your fingers, rotate it in your eyeball to judge. Yep,
and
you
I can
cannot
show
use
you a little
rotation.
trick that I use that helps a great deal too. You do have some play with the scanner itself, so if you don't want to reposition your sample, you can literally rotate your scanner.
Oh, I never thought about that. Yes, normally I pull the sample out and rotate. Yes, you can loosen the scanner set screws and then twist a little bit, give you a much smaller and precise angle.
Much faster too.
Much faster. Yes, yeah.
Yeah, we can do a walkthrough on scanner calibration. That'll be fun.
Yes, yeah, yeah. I do need that as a collection of my calibration. Yes.
And just in case anybody's wondering, the percent in the user's manual, so you can follow the instructions in the user's manual as well.
Yeah, because but you know the thing is that user manuals, if any users get into a little glitch, and it's always good to talk to someone. So yeah,
Very true.
yeah. Okay. If you have a question, please go ahead. If you don't have a question, I'll show you what is my plan for the next few sessions. As you can see, this presentation are hundreds of slides, and I have not even finished yet. A lot of little things. Talk about how to do your nanoparticles, your biological samples, and how to prepare biological samples and graphenes, how to run a sample which is a bit crystal, and so on and so forth. I can cover 3 sessions of sample preparation. It's probably just cover a very small part of it. Well, if we are running out of question, uh, so thank you for your time. I'm going to stay here a little bit so you can still stay here and ask me more questions. This channel will be open. I'm just going to, you just raise your voice and I can hear you. That we can keep talking. I'm not going to turn this off. I remember in one sessions I actually accidentally turned off a little bit early. Yeah. Yep, here's a message from Jason Marley. It's a nice trick, rotating the scanner to in the calibration. I actually never thought about myself. I'm so proud of myself that my finger is so precise. So I play with that like off. Yeah.
When you spend hours and hours and hours doing calibrations, you find little shortcuts to make your life a little easier.
So, yes. Steve, I have a question for you. So, who are the ones writing those menus? Were you the one that write those menus?
No, we actually had multiple people writing the manuals over the course of time, but we had hired some tech writers to do a lot of the writing. And what I found over time is some of the instructions are not entirely accurate or even remotely correct in certain instances. I don't want to go into the details, but when you hire a tech writer to write something that doesn't understand the product, you wind up with errors along the way.
Do you
So
see that we should write a book, but we should not write it, but using ChatGPT? Because I was playing with ChatGPT. It's like, wow, this is great. I don't need a team to do that. I can use ChatGPT, and I use my authentic, real experience and images. Those things are already there, and we could come up with a nice book. I just hate writing. That's all.
and yes, Jason, it will reduce the swearing coming from the room as well. Because it can be quite frustrating to get your sample squared up.
The swearing, yes, it is. Jason, you have the old AFM, and this old AFM was obviously built and designed by greatest one of the greatest AFM scientists with very delicate fingers, Tian Wei. So everything's kind of small. So imagine that someone is trying to operate this AFM, adjust everything, put the liquid cell together while wearing your winter glove. Think about it, right? This is the someone was faced when they tried to do lithium battery research because you're literally wearing a thick rubber glove, try to operate the instrument inside the glove box. I would cover that part. How do you do that? You basically have to rebuild the entire liquid cell, so it's a big chunk square.
Very true. I think STM is probably the most frustrating, right? Because if you uh, disengage your sample and you have to rotate your sample on on your stage and then reinstall it, you run the risk of um, crashing your tip every time you go in and out. And trying to rotate something 2 or 3 degrees by eye can be a little tricky. So yeah,
Two,
it's
three
best to
degrees. Yeah.
just rotate your scanner.
Yeah. Yes. Yeah, that's correct. And plus, STM scanner is. I have a hard time determining what is the correct orientation, anyways. There's no front.
Yeah.
AFM scanner has a front. Your STM scanner is a cylinder, and there's no front. You don't know which direction is X. Think about it, right?
Yeah. Yeah.
There's no X. So yeah, you got whatever you want, you do that. And then if you want to do a calibrate the atomic resolution, there's no grading, right? You don't have a
Yeah,
grading.
fortunately, with the scaling on the STM scanners, that's one of the things where you'll notice over time with multiple scanner sizes as well with the scan ranges. Um, Different scan ranges, say the 10 micron, if you were to scan at the full 10 micron range and then reduce to half to 5 micron, the deviation in your calibration isn't nearly as significant as if you reduce a 90 micron scanner to 45 microns. You know what I mean?
Yeah, yeah,
So
yeah.
the calibration will be still very, very accurate with um, your STM scanners. You typically want to calibrate at the atomic level and at the full range, but the deviation going from one to the other is nowhere near as significant as the large scanner trying to zoom in.
Yeah, large scanner zoom in is a kind of different story. You should write these things down and compile a book and put on Amazon because all the graphics is already done. And with ChatGPT, they will write. I don't need to write myself. See, you can write with me. You have a lot of things in your head.
I'll edit for you. How's that? I don't like writing either.
Yeah, I just have altogether 700 folders of data, and I mean, not all of them is valuable. Probably 10 to 15% of them has stories attached to them. Some interesting things, and then yeah,
Have you had an opportunity to look through any of those presentations I sent you yet?
Not yet, not yet. I will look at them after I like exhaust my own collections. I have tons of things my own. Yeah, I should look at it and then yeah. So maybe in next few sessions.
Yeah, I want to find a way to get those up on my website for everybody so that they're readily available. I know at least in the US, the installers used to leave those presentations on the PC when a customer had purchased a new AFM. So they're very valuable presentations.
Yes. So yeah, those are very good. And if you want to put on your website, I think you can export them into a PDF file, and then PDF the viewers can easily download them.
Yeah. I do want to clean them up and rebrand them, though. I don't want to be posting Agilent and Keysight presentations.
That's a good idea. That's a very good idea. Yeah, let me look through it and to see what's the best of way to do that. Yeah.
Send me your template. I like it.
Yeah, this template, yes. So it takes some time to set up. Once you set it up, you just everything cut paste into it. It's for adapt this template. So in other words,
Yeah,
this entire yeah.
send me yours because I like how it's got all of the branding at the bottom and pretty clean. I would advise don't use blue text anymore. It's extremely difficult to see.
Blue text, yes. My background is a little grayish. Okay. I can just send you this particular PPT or whatever PPT, and then you cut paste into it. It will adapt all the format. Okay,
There's
so
a
yeah, I'm sorry. Go ahead.
I was going to say there's an easier way to do that. If you send me one of your presentations, I'll clean it, wipe it all out, create a template, and then when you open another PowerPoint, all you got to do is go to the backgrounds and select templates, and it'll automatically change and rebrand everything for you.
Okay. Yep. Yep. I will send email some of to you right away.
Cool. All right, looks like it's just the three of us. Jason, nice seeing you again, buddy.
Okay, Jason. So see you next week, and hopefully see you here in more weeks. Uh, Good to have you, everybody here. Thank you very much. I'm just gonna stop now. Bye now.
Have a good week, everyone.